All right, we've got heavy duty week going on. So a couple of things. First announcement is regarding something brand new called chapter summaries. Okay, chapter summaries will now be starting. Oh, thank you. We'll start with this chapter and then move on to for all of the remaining chapters. Here is the deal. This is how chapter summaries work. Okay. You've been given a textbook. Okay, it's got a lot of good information about it. In fact, a lot of what you hear in class is what's already in here. Okay. Your job is also to read this book. Okay. Job is not just to do the problems out of it, but to actually read it. Okay. Now, when you leave this class at the end of the year, you have to leave this textbook here. Okay. But I want you to be able to take away with you the most important things that are in the book. Okay. So this is what I'm requiring of you. Your job is to write a chapter summary by extracting the most important parts out of each of the sections that are in the assignment guide. It's sort of like you're writing your own Cliff Notes for the calculus textbook. Okay? So, for example, for every section that is in your assignment guide, okay, you need to read the textbook and pull out the most important concepts that are in that section. A lot of times they're in bold or they're in a box already, something like that. But you have to summarize what is in here. When you should do this in a separate section in your notebook. Okay? After we finish chapter 1, unit 1 here, then we're going to move on to chapter 2, and you're going to do the same thing with each one of those. Every single chapter. That way, at the end of the year, you will have a complete summary of the most important topics that are in calculus that you'll be able to take with you. And if you're intending on taking second semester calculus, it will become very, very a powerful tool for you to have. Plus, you would have done it putting things in your own words as well. Okay? What's in the chapter summary is not just a duplication of what I say. It's what's in the textbook. Okay? You get a grade for this. And the grade that you get will be based upon how well of a job that you did of pulling the information out. And the chapter summary will be due on the day that we take the unit test. Okay? So, if you read through the advice from the former students, you may see somewhere in there they said don't do your chapter summaries on the last day before they're due, because it's kind of pointless. So you should be doing them as, like starting now, you should start to read the book and then pull the stuff out. Megan?
So when you say like how they're divided in sections, like 1-1, so we pull the most important part out of 1-1.
Out of 1-1, then 1-2. So you'd maybe have like, I don't know, perhaps like 4 pages from this first unit, and it's all of the most important things from 1-1, 1-2, 1-3, 1-4, and so on. Mackenzie.
Is it like, you find it like where you're like writing about it, or is it more or less writing down like the rules and examples?
I would copy down the rules, okay? And if you feel like you need to write an example that demonstrates that, then copy down an example. But I don't want you to just copy every single thing out of the textbook.
So it doesn't really have to be the best like explain it in our own words?
It can be. Look at it this way. Around April, after you've done all of the chapters, do you think this might be a powerful tool to study from for the exam? So you're going to write this for you. You're not writing it for me. I'm going to give a stamp of a grade on it, but It doesn't help me at all. It has to help you. So put it into a form that it makes sense to you. Yeah.
Should they be a certain length?
Whatever it takes to get the job done.
Can they be typed?
They can't be typed. And they have to be legible.
Yeah, exactly.
If you can't read your own writing, that's bad.
So it's only the sections on the whole.
Yes. So for example, 1, 2, 3, 4, 5. There are 5 sections on this. You need to write the chapter summary for these 5. You have to have all of these 5. Yeah.
Are we like handing our notebooks out with it?
Yeah. You'll hand in your notebook on the day of the test, and then I'll grade them, and then I'll get them back to you. So you're not going to tear them out. Yeah.
So for typed ones, you want us to hand you the printed copy or an email?
Actually, I prefer a printed one because then I can write on it. Yeah.
And so you can have like bullet points and
Yeah.
everything.
Right. Right. A summary that you feel that you can use. It's very good. You're asking lots of questions. That's what this is about. Yeah. The tests end up being a really important part, and they will be a in-class, one class period test that is where you have to do all of the work. You get partial credit for things that you don't get right. It's not multiple choice. And we'll maybe clarify more as that time comes along. Well, whatever it takes to kind of do a whole class period. And it'll be a variety. It could be anything that we've covered in the whole chapter. Okay? Very good? Yes?
Do you have like semesters, like in semester 1 exams, they can be like a deal for all the next people?
Yeah, the semester 1 exam will consist of problems that can come from anywhere in the entire chapter, or in the entire semester. Yeah.
What about that other like textbook thing that we got? Oh yeah.
That booklet thing?
Yeah.
That big book?
Yeah.
That you can just use as a review. You don't have to write any chapter summaries out of there. But you'll see, like, we're going to be focusing on limits now, doing limits analytically. There's a whole section in that book. So if you wanted to look at that and see how they explain it, you can do that as well. So far, so good? Awesome job of asking questions to clarify. Way, way better. All right, we're going to do 2 things now. I'll take questions from page 54 here while people are getting answers to these 3, being able to justify them. And then we're moving on. Make sure you get your video approval form in ASAP. All right, so get me 3 answers to those and put up questions from page 54. You can be my escape artist if you want to be. All right, then get answers to these 3. Okay, we have 1, have a really good handle on how to find a limit graphically.
Yes.
Okay, that's a must. Today, what we're going to do is we're going to take away the graph. Now we're just going to find limits with just the functions themselves. Okay, so I just see a couple of questions. Actually, you just see number 54 that we need to go through. So let's take a peek at that one. Now remember, this site exists. I sent you links to both of these, and the Slater one, that one exists too. So remember to take advantage of those. Okay, 54 says this. If f of 2 is equal to 4, can you conclude anything about the limit of f of x as x approaches 2? Okay. True or false? Can you conclude anything? No, you cannot conclude anything. Why not? It could just be a point. Okay. Now, here's how this works. In this class, an answer all by itself is not good enough. You have to justify yourself. Okay? It's good for us here, but it's also good for you in many aspects of your own life. If you want to convince people of something, you need to justify yourself so that you can actually convince them. So this means this. That's the only thing that it means. So the function, we don't know what happens, what it's approaching, other than that. It could be a graph that looks like this. Right? Where the limit would be 2, and even though the functional value is 4. But it could look like this. Okay? So here the limit is equal to the functional value, but here the limit is not equal to the functional value. Okay? So the answer, can you conclude anything about the limit? No. Okay? It's just that simple point. Yeah. You can say something along the lines of that f of 2 equals 4 is a point. It has the coordinates 2, 4. And we know nothing about f of x as x is approaching 2 from either the left or the right side. Yeah.
Oh, this is kind of on the homework, but I forgot to put it up. If the dot, like, where you're trying to find the limit, say it's on -1 on the left side.
Yep.
Would there be a limit on a parabola if it's, like, more on, like, the curved end of it? Because it's going up before it comes down, like your values, your y values? I don't know if this is making any sense.
No.
Okay, so, like,
Yeah, come on, Maria.
So, because I think this is like number 10. So if you have like your point right here, you're trying to find your limit. Does that have a limit because your y values are going up before they come down?
Oh, great question. If I'm finding the limit right here,
Yeah.
okay, maybe at -1, and even though there's a hole here, can we still have the limit here?
Yeah,
That's
or
the
like even
question.
if the hole's gone, like because they go up before
Right.
they come back down.
The thing about the limits is we only focus on what's on a window that's very close to it.
Okay.
So we don't really care what happens all the way around the outside.
Okay.
So it's just narrowing in actually extremely close to it. Infinitesimally. All right. Good. Let's move on. Section 1.3 is where we're going today. We're now going to strip away the graph and find the limits analytically. Forgot the swivel. What would I do without you guys? Be out of a job. Okay. In this whole section, this whole section, we're finding limits analytically now, but we may borrow a little bit of graphic in our process. Bitsy first.
But I think with the chapter thing, like the assignment guide, that's 3.5 on it. Do you want that in chapter 1?
Yes. Yeah. There's 3. Is it just 3.5? I thought there maybe was one more. Yeah. Whatever is on that list. See, I don't like the order that the textbook does it, so I put them in my own order. Yes.
So you put 1.2 and then you put 1.3. It says that 1.2.
Oh, yeah. I think it's 1.3, isn't it? Yeah. Ignore that 1.2. I should have never told you guys to challenge me. No.
That looks like funny.
Okay. So, but see, that's the only way that everybody knows exactly what's going on. So let's identify what we have here. There's no graph. Okay, can we still find the limit? And the reason is we make sure we identify here. This 2 is the number that we are approaching. Okay, so that's kind of a note to self. This thing right here is the function. Okay, we don't have a graph for it. Okay. So the first approach that I always want you to take is I want you to try to visualize it. Okay, so let's visualize this. Visualize. And can you tell me what this function looks like? It's a parabola. What else about the parabola? Careful. It shifted up 3. Okay? So this is the parabola here. Okay? Are there any holes in this graph? Are there any asymptotes? No. Are there any jumps? Is there any place that if you plug a number in, you don't get a number out? No. So that means I can approach 2 quite nicely, and if I plug in 2, I'm going to get the actual number that corresponds to it. Okay? So plug in a 2, and I get 7 out. And so my answer is 7. Nice scale. Okay. So wait a second. We're gonna make some observations here, and the observations are going to be our rules. Okay. Because I don't like just simply writing out rules and then explaining them. I like for us to think about them, and I like making them up. Okay. All right. Can we make a rule yet? Okay. So let's we can say if there are no asymptotes, no holes, no points of what we call discontinuity, then you can do what? Just plug it right in. Okay? So we say, here's a rule. If f, the function, is continuous. And when I say continuous, I mean that it's continuous on the whole entire domain. Okay? On all of negative infinity to infinity. So if f is continuous, then we can just plug in the value to find the limit. Bada bing, bada boom. let's see what we got here. So that means this, if I say okay. No biggie. Are there any holes or asymptotes on the sine wave? No. Any holes on the square root function? No. Any holes on the cosine function? No. So if I took all three of these and added those first two and subtracted those two, I would still get a y value for every single point. This function, even though it's kind of wacky, is still continuous. So we can just plug it in. Watch. This means we're going to get the sine of 4 times pi over 2 plus the square root of pi over 2 minus the cosine of 3 times pi over 2. And we can get the answer to some of these. This is the sine of 2 pi plus the square root of pi over 2 minus the cosine of 3 pi over 2. We're trusting this limit now. We're trusting this rule. If the function is completely continuous, bam, plug it in. Because the limit will always equal the functional value. Always. Okay, sine of 2 pi. Zero. We can leave this square root of pi over 2. That's fine. There's nothing wrong with that. Cosine of 3 pi over 2. 0. You're at the bottom. Cosine is the x. So the answer to this is the square root of pi over 2. Just like that. No problem. Okay. So if the function is continuous, you can just plug it right in. Okay, let's do some more. Swivl. Sorry. I don't know if I'm ever going to get used to that. Follow me. Yeah, that's what we need. Okay, new problem. Okay, what kind of function is this? Is there a name for this? It's called a rational function. Okay, rational functions are functions that are made up of a fraction where there's actually one function in the numerator and there's another function in the denominator. Okay, does this thing have any holes or asymptotes or jumps? Yes, it does. Where x equals 3. X equals 3 is bad because if you plug in an x equals 3 into that, you're going to have 0 in the denominator. Now, do we remember if it has an asymptote or if it has a hole? This particular one's a hole. Why? Because we can cancel it. Okay, so watch what happens here. In this particular problem, if I try to plug the 3 in, just so you know, if I were try to, so don't copy this down, I get 3 squared minus 9 over 3 minus 3, which brings us back to our big division symbol. Okay, 0 over 0 is really, really bad. Okay, it's not just something over 0. 0 over 0 actually has a name. It's something called indeterminate form. Okay, that's something to know. Indeterminate form is something like 0 over 0, or infinity over infinity, or 0 over infinity, or infinity over 0, those combinations are extra bad divisions. So they get a special name. So this is a problem, so we can't do that. So last year you would have learned that to find if you have an asymptote or a whole, what you do is you try to see if you can cancel. So this means we're going to factor the numerator, and when we factor the numerator we get x minus 3 times x plus 3. That's our classic difference of two squares, x squared minus 9. And this is over x minus 3. Okay. So the numerator factors into this. Okay. Oops, my bad. There we go. Okay. Put that hand up. This is the kind of, I'll make mistakes like that all year long, so you got to catch me. So because the numerator is now factored, we can look for the factors that's going to cancel. Here, x minus 3 divided by x minus 3 is 1. So that gets replaced with 1. And this limit then gets replaced. That what we're doing here is we're actually trying to find the limit as x approaches 3 of this new function, which is just x plus 3. Now look at, what's this function? It's a linear function. It's a line. Okay, does it have a whole or an asymptote? No. So that means we can go back to rule number 1. If f is continuous, just plug it in. So here, the way that we do this, just so you see the notation, this is critical. We're now going to find the limit, and that means you drop the limit notation and you replace the 3 with the, replace the x with the 3, and that's where we get an answer of 6. All right, pull out your calculator. I'm going to justify this with a calculator. Type in that function, the x squared minus 9 over x minus 3. All right, so clear everything out here. And we're going to put in x squared minus 9 over x minus 3 as the function. And you have to use your parentheses properly. It's x squared minus 9 over x minus 3. And then just so we have all have the same picture, I want you to press zoom and then, oops, zoom, and then press the standard one, which is number 6. Okay. Everybody get this line? Get this line? Okay, so here's a point. Sometimes you look at this, you see x squared minus 9. How many thought it was supposed to be a parabola at first? Okay, or it had to have some parabola in it, right? Because it's got x squared in it. We're always taught that's what it is. But it's the fact that we're dividing by this that makes the difference. So that line right there, take a close look at it, and in your head, just what is the equation of that line? Just by looking at the slope and the y-intercept. Looks like it's got a y-intercept of 3 and a slope of 1. Okay, so the equation is really y equals x plus 3. Agree? That's this. Okay, it's what you get after you cancel. So the trick is to see this is when you cancel the numerator and denominator, what value that makes that 0, that's where there's a hole. Okay? So this tells you that there's a hole at x equals 3. And what's left over is the actual graph. What's left over is the actual graph. So, look at this. Hit the trace button. Okay, and of course we can trace along this line, but plug in 3 and tell me what the y value is. Okay, there is none. Because what's really going on here is this is a graph of y equals x plus 3, but there's a hole at x equals 3. So if I were to graph it here, 1, 2, 3, there's actually a hole. And what is the y-coordinate that it should have been? 6. Because remember, we just figured out the limit to this one was 6. Because as we were approaching it from the left and approaching it from the right, we would actually, we can say graphically that the answer to the limit is 6, but we did it analytically and we got the same answer. Make sense? Yeah.
So you're just going to take your number that cancels and set that equal to 0 hole?
Well, you could have more than one hole too, and it does depend what you're approaching. Like if I said x is approaching 2, and you're used to just doing that, then you're missing the point that we can actually just plug it in there, and the answer isn't the 6. Okay? All right, let's try another one like that. Limit as x approaches -3 of x squared plus x minus 6 over x plus 3. Yeah. Yes. The limit is what would be the expected y value as you let x approach this value. Okay, so if you move ahead on this one, that's fine. I don't mind it if I put a problem up there and you want to just go ahead and go right at it. I'm going to go through this one. So, can we plug the -3 in and get the answer? No, what happens, I can see for sure right now, if we plug in the -3, we're going to get 0 on the bottom. Okay, so that's no good. Okay, we don't even care what happens in the numerator. So if we can't plug it in, can you visualize this thing? Can you picture this in your head? Not really that easily, okay? So what we should do is we should try to see if we can factor this thing and see if anything cancels. So limit as x approaches -3. Okay, put on your factoring hat here. That's what I got. Okay. You will have to know how to factor on the AP exam. Okay. Alrighty. So I spy x plus 3 canceling with x plus 3. And because we canceled one with the top with one on the bottom, what does that mean that occurs? There's a hole. And where is the hole? At -3. Okay. So there's a hole at x equals -3. Okay, so then we look at what remains, and we have the limit as x approaches -3 of x minus 2. That's it. Everything else is gone. So this means that we can now proceed to find the limit. This is a linear function, which there's nothing wrong, there's no holes left over there, so now I can take the limit, is what we call it, and plug in the -3. So it becomes -3, then minus the 2. Notice this is where I drop the limit notation. Okay, that's where this thing goes away, is when I do this step. Okay, mathematically, that's how you got to see it. You have to write down the limit every single time until you actually take the limit. And -3 minus 2, the answer is -5. Okay. So the graph of this goofy thing is actually a line. It's a line y equals x minus 2, and there's a hole at x equals -3, and the y coordinate where the hole is at -5. Right.
Okay.
It's the expected value. It would be, that's where if there was a value, or we can say the hole appears when x equals -3, and the hole occurs where y is equal to -5.
You were so good at it.
You want to watch this one. One of these days.
You were so good, and now all of a sudden you...
Okay.
Video.
All right. Limit as x approaches 3 of 5. That's kind of weird. Stop and think of what it means. Okay, answer? 5. Why? What kind of line is it? Horizontal line. If you were to graph this thing, wouldn't you all agree that it's the line y equals 5? So it really doesn't even matter what I approach, the answer is always going to be 5. If it was a vertical line, then we wouldn't be able to put anything here.
So you can't...
So we won't take any limits on a vertical line. Because it can't be expressed as a function.
Yeah.
Okay, so that means this. C. Okay? Again, this fits exactly the same thing that we did here. It's just, whoa. It's just that my function is y equals c, or better yet, it's c of w. Because I use the w here rather than x. Okay, so it's really the function c of w. Okay. The limit as x approaches 8 of x. Very good. Kayla, what is it? 8 is the correct answer. Why? Okay, we can plug it in. Isn't this the line y equals x? Okay, so if I plug in an 8, I'm going to get an 8. It's continuous, and so we can plug them in and find it in that way. That make sense? So, with every single one of these problems, this is our first rule. Okay, if f is continuous, plug in the value to find the limit. And then we'll say the second one here, if f is not continuous, then factor and cancel.
What if you can't do that?
Then we're going to add to the list. Okay, you have your next homework assignment, and that is going to be due Thursday. Part 1,